when we're looking at birds and animals, there's, all different kinds of names and primarily focus on the genus and the species. So I always think it's interesting where these names come from and kind of the history of how that all came about. And a really good example of this is penguins, because in the modern world, we all know penguins. We all love penguins. And there is a genus for birds called Pinguinus, but penguins are not in that genus, and they're not even really closely related. So that's what we're going to go over today, why penguins are not in the genus Pinguinus. When we are learning about animals in the natural world, we know about the North and the South Pole. Those two polar opposites are the cold places in the planet. And one of the things you learn as a kid is that, well, in the North Pole, you have polar bears and other Arctic animals. At the South Pole, you have penguins and other Antarctic animals. But what if I told you that the real penguins were in the north, and the only true penguin came from the North Atlantic Ocean? So the world's first penguin is a bird today we call the Great Auk. Now, the Great Auk, Pinguinus impinus, was a large flightless seabird that used to live in the North Atlantic Ocean. They were about 30 inches tall, so a couple feet high, and they weighed like 10 to 13 pounds, but they were the largest mammal of the auk family, which includes puffins and razorbills and what we call the alcidae. So these ones were the only flightless members of that family. So they were birds, but they didn't fly. They swam in the ocean. So characteristic of the auk was its black and white plumage. It had a white patch on the front of its eye. It would grow during the winter months, and it was an expert swimmer who, like modern day penguins, dove into the ocean and was good at hunting fish and crustaceans and other, ocean animals. Now, most of the year, they lived out in the open water. A group of penguins is called a raft. So these large rafts of these ocean-bound birds would swim all throughout the North Atlantic. So from Canada up to Greenland, Iceland, down the coastline of Europe, these animals were just something that sailors would see, but it wasn't all that often they came up onto land. But they would during one specific time of year, the breeding season. So during the breeding season, the auk would leave the ocean, they would find a rocky outcrop, and then they would build a colony there, and they only laid one egg per year. So that's all they had to do was just once a year, go up onto land, reproduce, and then back to life in the water. Now, at the time, the Great Auk was known by many different names across Europe. And the English name was the garfowl, which probably comes from Icelandic gurfugl, which just means spearbill, kind of referencing the sharp beak that the birds had. In Welsh, they might be called penguin. So that's one of the origins or possible origins of the first usage of penguin. And penguin just meant white head. But also in Latin, pinguis kind of means fat or plump. And so Spanish, Portuguese, French words, all of these kind of Romance languages that came out of Latin, they all use different versions of pinguino, pinguum, pinguin, and that's another possibility of where the common word penguin came from. So all across Europe, different cultures, different regions had different names for this common bird that you would see swimming in the water. So where do we get all these different names, scientific names specifically for plants and animals? Well, in biology, we call that taxonomy. And this is something you'll learn kind of through grade school, middle school, high school. But I find it interesting how the history came about. During the Renaissance, and then you have the Age of Enlightenment, all this scientific advancement is happening in Europe. But again, each country kind of has different names for different animals. So take your common horse, for example. English, it's a horse. French, it's cheval. And Spanish, they are caballo. So when scientists during the Age of Enlightenment were communicating across borders, they started to realize, oh, these are the same animals, but we have different names for them in all these different countries, and it would just be a lot smoother and easier to communicate if we all just kind of unified this naming system. A lot of these scientists and academics were reading, Greek, Roman, ancient literature, and so they all kind of had a general familiarity with Latin. So that's where we start to unify naming, just kind of simplify everything instead of English, Spanish, French, Portuguese, German. Everyone just kind of agrees that Latin is going to be the base of naming animals. So our horse, our cheval, our caballo, all of them in Latin are equus, just the Latin word for horse. So this is the start of something we call polynomial nomenclature. Nomenclature just meaning name, polynomial meaning many of them. So you had a label for the animal, but then you would also, or scientists would also use like a series of descriptors to also kind of write out what that animal looked like. So for specifically a brown horse with a long tail and solid hooves, we'll translate all that into Latin. You might get something like equus, ubatus, fuscus, cauda, longa, ungulus, solidus. So it was a good way to describe the animal, but it wasn't a great name. These were more like sentences rather than actual specific names. But that was kind of the first step towards unifying this naming system across Europe. But that did present a problem. Those long names, while descriptive, were tough to remember. So something as simple as a common buttercup might end up with a long name like Ranunculus flore pleno, Calucibus reflexus, folius duplicato lobatus. A lot of words to say, a lot of words to remember. Caspar Bauwin, or Gaspard Bauwin. Again, different places have different pronunciations for these words. In 1623, he was a botanist, and he was classifying thousands of these plants. So you can imagine if you're trying to write the name of thousands of plants, and each one of those names is a sentence long, gets very tiresome and tedious. So Bauwin just started kind of shortening everything up, and he created the binomial system. Just a generic label, and then a specific kind of that animal. So this is where we get genus and species from. The generic group or class is that genus. So in horse, equus. And then the specific label or the kind of animal would become the species. So Bauwin was the one who really just shortened all the polynomials down to a genus and a species. And then about 100 years after Caspar Bauwin creates the binomial system, another naturalist named Carl Linnaeus is growing up in Sweden. Linnaeus loved plants, and if you love plants, you usually went on to study medicine. So he would eventually go on to study medicine in the Netherlands, where he encountered works from Bauwin. And he realized that this shorter binomial nomenclature was much easier to write out and remember, and he would also go on to categorize thousands of plants throughout his life. Just having a genus and a species made a lot more sense. So Bauwin would be credited as creating the binomial system, but Linnaeus is the one who's remembered as popularizing it. And this would continue on into the standard naming that we still use today. So, good example of this is just look at modern day sloths, because even with a genus and a species, even though you're losing those long descriptive sentences, you can still be descriptive with this binomial system. Linnaeus has a sloth named after him, Linnaeus two-toed sloth, but the scientific name is Colipus didactylus. So, colipus is from Latin colos and pus, which means lame foot, essentially kind of alluding to the fact that sloths are kind of slow and not great at walking around. Didactylus is 2 fingers. So in sloths, you've got 3-fingered sloths and 2-fingered sloths. And so the ones that have 2 fingers, didactylus, easy to remember, and also a good description of what the animal is, a slow-footed 2-fingered sloth, essentially. Sloths of the 3-fingered variety usually fall into the genus Brodopus, which also means kind of slow-footed. But here you have other descriptors like Brodopus variegatus, or the brown sloth that has variable color to its fur, good for camouflage. There's also Brodopus torquatus, which is the collared sloth, or the mane sloth. So yeah, torquatus, adorned with a collar, good description of the sloth that has like dark collared or like a dark mane around his neck. So you can see how even with a binomial system, you're not always losing that descriptive side of the naming, but you're shortening everything down, making it a lot easier. 100 years after Linnaeus, a new type of two-toed sloth would be discovered by a man named Carl Hoffman. And he named it Colopus hoffmanni. So here, the species is not a descriptor, it's named after the scientist who discovered it. And this is a process called eponymous naming. Naming plants, animals, things after people of significance. So a good example of this is Rhinoderma darwini, or Darwin's frog, named after Charles Darwin. Another fun one in the modern era is Phytolae harrisonfordi, or an ant named after the actor Harrison Ford. So with the binomial system, you have the genus and the species, and the genus is the label. The species, you can use that word to describe the animal, but at a certain point, you're getting such a specific, refined, small thing that the second part doesn't really matter what it is, and that's where this eponymous naming comes from. Just naming the species after oftentimes whoever discovered that animal and realized it was distinct and different from others, or the scientist kind of gets to name it after someone they like the actor Harrison Ford. Going back to Linnaeus, in 1735, he publishes his first paper, Systema Naturae, where he kind of begins to outline his hierarchical system of naming different animals. Then in 1753, he publishes another paper, Species Plantarum, and that just lists every known species on the planet using the new binomial system, which really solidifies its place in science. And basically, a lot of the names that Linnaeus wrote in 1753, we still use in the modern era. And to maintain the descriptions or the diversity, Linnaeus also categorized things using hierarchy. So genus and species are kind of the base level of how you name animals, but there are other levels to it. So genus and species are kind of at the bottom of the hierarchy. Above them, Linnaeus created the order, which kind of groups animals based on similar behaviors, such as like carnivores versus herbivores. Above that, you have the class. And the class more broadly groups animals into, well, are you warm-blooded or are you cold-blooded? Things like that. And then above all of that are the kingdoms. And this is Linnaeus's broadest stroke. This is where basically you either have plants, animals, or minerals. Now later minerals would be taken out and they're not really organic, but that was the way Linnaeus kind of viewed the natural world. Everything started with plants, animals, minerals, and then over time it would filter down into one very specific species. So after Linnaeus, that lays the groundwork for taxonomy. And then another 100 years later, Charles Darwin's theory of evolution kind of shifts taxonomy away from animals that look the same to more grouping them based on evolutionary history. Around the same time, other naturalists and scientists realized Linnaeus' hierarchy is good, but we can add a few more levels into it. So this is where the family and the phylum were introduced. A naturalist who is credited with this is a man named Ernst Haeckel. And then in the 20th century, we had the modern synthesis of genetics and evolution. So now we've built upon Darwin's work. We've added in DNA and looking at genes and seeing how animals are closely related at the genetic level. So a 20th century scientist named Carl Woese in 1990, he proposed adding another hierarchy above kingdom, the domains. And this step-by-step process is how we got modern taxonomy today. So at the very top of the hierarchy now, we have the three domains: bacteria, archaea, eukarya. So this is just broadly speaking how different we are from bacteria. Does it have a nucleus? Does it not have a nucleus at the cellular level? Archaea are kind of small like bacteria, but they're a little bit more complicated. They live at crazy extremes of the earth, like at sulfuric vents at the bottom of the ocean. So they're not really something your everyday typical person needs to worry about, but they are out there in the animal world. Then below that, we have the kingdom. And minerals we've taken out. Those are over in geology. They're inorganic. So we have the animal kingdom, the plant kingdom, the mushroom kingdom. And that helps to define different organisms based on things like plants have a cell wall, animals do not, how mobile they are, what kind of food and nutrition they obtain. So that's Very broad, but not quite at that high level of the domain. Then below that, you've got the phylum, and this starts to categorize organisms based on things like body plan. So think of vertebrates versus invertebrates, those broad categories. Within that, the class splits up the phylum by specific traits. So mammals are the warm-blooded, fur-covered animals that produce milk. Below that, you find the order, which helps to even further subdivide those classes. So you can have mammals, but are they carnivores or are they herbivores? That's where the order divides things. Below that, you have the family. And this is grouping similar organisms all into one family. And this is what a lot of people know, like the dog family, canine, the cat family, feline. Then below that, we're back to the genus, the generic label for a group of similar looking organisms. So think horses, zebras, and donkeys. And then below that, you finally have the very specific label, the species. So again, going back to our horse example, we've got the Equus cabayus today is the genus and species name of a common domesticated horse. So that is the hierarchy that we call taxonomy. Domain, kingdom, phylum, class, order, family, genus, species. And from the top down, it just goes from the very broad all the way down to the very specific. So what does this have to do with penguins? Well, we're getting there. And we talked already about our first penguin, the Great Auk. Where is it? What happened to it? Where did it go? Why isn't it around anymore? Well, extinction happened. But it wasn't ancient extinction like the dinosaurs. These animals were around in the modern era. Even Carl Linnaeus himself talked about penguins in Systema Naturae. And at first, he grouped them with the other auks, the other Alcidae, these birds that all had sharp bills and were known in the North Atlantic. But over time, the Great Auk kind of stood unique. It was the only member of that family that couldn't fly. It was bigger and different from all the other Alcidaes. So eventually, in 1791, Linnaeus moved them into their own genus. And this is where we get Pinguinus. And again, it could be from the Welsh penguin for white head, or it could be based on probably more specifically Latin, because that is what all of this is based around. And the Latin pinguis just means fat or plump. So this is where we finally get the first true penguin, the Pinguinus impinus, the plump, flightless bird that lived in the North Atlantic. And its closest cousin would be something like the razorbill. So there are modern cousins of this animal still alive today, but the Great Auk itself, well, going back hundreds of thousands of years, it's been good food. Those fat, plump birds were hunted by Neanderthals. We found bones with butcher marks on it that tell us that, yes, Neanderthals and early hominoid species, they were eating the Great Auk. And you even see auks represented in some cave paintings around the coastline of France. Their eggs were also very massive. So think kind of like ostrich eggs, big protein-rich capsules that humans would often eat. But for hundreds of thousands of years, humans were on land, auks were in the ocean, and they were hard to reach. Even their colonies were on these rocky outcrops that were way, way, way off the coastline. So humans might have eaten the Great Auk, but it wasn't overhunted. It wasn't super easy to get to these animals. So for a long time, there was a balance. But then in the 1500s, the Europeans start crossing the ocean. They're going from Europe over to the New World. They're crossing the North Atlantic. And at first, the auk is kind of like a navigational tool. Since they lived in the ocean but near the coastline, well, they would travel hundreds of miles of open ocean, thousands even, and then all of a sudden you'd see those big rafts of auks and you knew, okay, the shores of Newfoundland are pretty close to here. But also, to get across the ocean, if sailors could, they would capture and kill huge rafts of these animals. They would eat fresh whatever was available and whatever they could fill themselves with. The rest of the meat, they would salt and store for these long transatlantic journeys. Now, the feathers were initially discarded. No one's eating feathers, but eventually someone realized, well, we can put those feathers in pillows, so they became more and more popular for their meat and their feathers. Also, their eggs were being raided by settlers in the New World, and it wasn't hard to predict that over time, this overhunting, overexploitation, this would lead to the downfall of the animals. They only laid one egg a year, and they mated for life. So if you killed that and ate that egg, well, there goes the next generation. If you kill one of the auk's mating pairs, well, they're not going to reproduce again. So just hunting and egg raiding led to the animal becoming pushed to the brink of extinction. And in the 1830s, there was only one colony of the Great Auk left. They were on Great Auk Island, or in Iceland, Garfuglasker. Now, this was a volcanic rocky outcrop kind of far off the coast of Iceland, so again, hard to reach place, good refuge for the birds. But unfortunately, due to Iceland's volcanic activity, eventually that rock submerged into the ocean. And the last few auk that were left had to move to an island a little bit closer to the coastline of Iceland called Eldey. Now, at the same time, people around Europe knew this animal was going extinct. And for decades, museums and private collectors had been buying eggs, bones, taxidermied versions of the animal, and they were becoming pretty pricey. So when that last colony moved to Eldey, people rushed to the island to basically harvest the last of the animals, stuff them, and use them as museum specimens. Instead of thinking, oh, we can protect these animals and study them as living organisms into the future, they just said, you know what, it's too late. This animal is going extinct. Let's just kill the last few that are left and put them in our collection. So that is how the Great Auk went extinct. It had existed for hundreds of thousands, maybe even millions of years, going all the way back into evolutionary history. But over the course of just less than 300 years of people traveling these transatlantic voyages, the auk just disappeared. So what does this have to do with the southern hemisphere penguins that we know and love today? Well, around the same time, 1831, a ship is leaving England on a route to the southern hemisphere to navigate the waters, look for new trade routes, map out the coastline of South America. This ship is called the HMS Beagle, and on board is a man named Charles Darwin. Now, at first, he was hired to be the naturalist. So as the sailors looked for the trade routes and mapped out the coastline, Darwin studied what kind of geology, biology, and natural history was in the New World. So as they were sailing south, one of the animals Darwin encountered was a swimming seabird with black and white plumage, and it looked very similar to the penguins he knew back home. So they also start using the word penguin to describe these seabirds of the southern hemisphere. And even in Darwin's journal about his trip, he would talk about all the different penguins and birds that he saw along the way. So this trip, the voyage of the HMS Beagle and Charles Darwin, that would be Darwin's inspiration to go on and write The Origin of Species, which was the foundation for what we call evolution by natural selection today. And what Darwin observed over the course of his trip was that in some places, many different types of animals, if you look closely, all kind of came from the same common thing or the same common ancestor. So the classic example was Darwin's finches. You can look at finches around the Galapagos Island and realize, oh, all these are the same type of thing. They're all finches, but some of them have bills designed to tear fruit away. Some of them have bills designed to crush seeds. Some of them have bills designed to suck nectar. And all of these different ways of getting resources over the course of many different generations has led to the diversity of these animals that he's seeing on these islands. So is that what happened with the Great Auk and the Southern Hemisphere penguin? Are they just two long-lost cousins from the same lineage? Actually, no. Even though they look very similar, they're not closely related. And Charles Darwin's work on evolution would eventually develop into sciences that helped us understand why these two birds look and act so similar but come from vastly different backgrounds. So we've got our Southern Hemisphere penguins and our Northern Hemisphere, the Great Auk, both of them black and white, flightless seabirds, but this is all the result of something we call convergent evolution. And the classic example of convergent evolution that you learn in biology class are kind of birds and bats, two animals that have both developed traits like wings that allow them to fly, but bats are mammals coming from tree-climbing, warm-blooded organisms, whereas birds are more descendants of ancient dinosaurs, essentially. But another good example are dolphins and sharks. Both dolphins and sharks have an effect called countershading, where their back is darker and their front is lighter. So when they're swimming in the ocean, while looking down on them, they kind of blend into the dark ocean floor. And looking up, they blend into the bright sunlit sky. And so that kind of coloring is something we call countershading. And it's not something that is unique to just sharks and dolphins. You can find this in orcas as well as our Great Auk and our penguin. So that black and white color that's iconic of these birds is basically the same thing. It's just easier to hide in the ocean if you have a dark top and a lighter bottom. So over time, organisms just develop these traits. For the auk and the penguin, both of them came from ancient birds, one in the northern hemisphere, one in the southern hemisphere, that both decided to jump into the ocean and go fishing. Just random chance meant some birds had stronger lungs. They had shorter wings. Some of them developed web feeding. All of these features helped boost their ability to get food and resources. And the more food and resources they got, the more likely they were to reproduce, passing those genes and those traits on to the next generation. So this goes back into Darwin's theory of evolution and organisms over time inheriting these specific traits from their ancestors. Penguins in the south, Great Auk in the north, both of them are birds looking to swim into cold, freezing water, which means both of them developed these similar characteristics. So selective pressure is key to Darwin's theory of evolution. It's not nature designing and thinking, oh, like this will be great, this will work well. It's more or less just kind of random things happen. Random genetic mutations cause different phenotypes to appear, different body features. If those body features help that animal collect resources and reproduce, well, then maybe that genetic mutation is going to be passed on to the next generation. And if it mutates again, becoming unproductive, well, that lineage is going to die out. So this is how we kind of trace evolution over time. If you look at these selective pressures, things from the environment like cold, frigid water, you can see how animals on opposite ends of the earth kind of develop the same phenotype, the same look over time. It's just the most well-suited body plan for both of these birds to be the most successful at hunting and reproduction. When we're looking at the Great Auk and we're looking at the modern day penguin, well, going back to the taxonomy, the hierarchy of the animal kingdom, we can say both of these organisms are birds. They're both in the class Aves, but after that, they diverge. So the penguin and the Great Auk may look like one or the other, but they come from totally different backgrounds. So below birds, looking at the Great Auk, their order is Charadriformes, whereas penguins are in a completely different order called Spheniformes. So they might both be birds, but that's about as closely as they're related. Now, through taxonomy, that's what we can look at. Just kingdom, phylum, class, order, family, genus, species, and knowing that the higher up on that scale the divergence happens, the more widespread the relationship is. But can we get deeper? Can we get more specific? Could we build a family tree of this evolutionary history? We can. It's called cladistics. And this is like the family tree of evolution, where all these different organisms came from. You can trace them back to their different common ancestors. And this was started in the 1950s by a German entomologist named Willi Hennig. The idea of cladistics in his work Phylogenetic Systematics. And this is where he was studying Charles Darwin's theory of evolution and realized this was a much better way to group and classify how organisms were related, not just looking at what they look like and what they act like, because through convergent evolution, that can be deceptive. But if you can trace their shared traits back to a common ancestor, you can start to make different branches in this family tree. So a cladogram is that family tree. It's kind of a simplified version of how different organisms are related. The branching part is called the node, and that node usually indicates some kind of shared common trait that we might not actually know what the ancestor was, but we can tell something was there. We just haven't found it in the fossil record yet. When we started really studying DNA in the 20th century, adding in genetic relationships, also in the 80s and 90s, when we had computers who could do a lot of these calculations and create these cladograms, that made things much more easy, and it basically became a standard part of evolutionary biology. So today, when you're looking at how different organisms are related, it is important to know the kingdom, phylum, class, order, family, genus, species, the taxonomy, and the hierarchy. But it's also important to know where those divergences occur, and this is most easily seen through cladograms. So what does the bird family tree look like? Well, when we place the penguins and the Great Auk on the cladogram, the Spheniscus and the Charadraformes are related, but you got to go back about 3 to 4 different nodes. So in both sides of this family tree, there are many other birds that look wildly different, but are more closely related to things like penguins and the Great Auk. So in Charadraformes, you have the Alcidae, and this is what we're talking about with the razorbills. This is also things like puffins and the common murre. Outside of that, the next closest cousins are other seabirds like seagulls and skuas. Now, for the penguins, their whole order, Spheniscus, is just penguins. That's all that's in that one order. So within penguins, there are 18 different species across the 6 different genera, or the different genuses. And you can commonly categorize them as crested, banded, bushy-tailed, large, yellow-eyed, and little penguins. But that whole order, Spheniscus, is just modern-day penguins. But outside of that, you can also group different organisms into a similar branch of that family tree by creating things like clades. So the clade penguins belong to is called Ichornithes. And this includes other seabirds, but now we're talking about albatross, petrels, loons, and pelicans. So it's kind of crazy to think that a huge, massive flying bird like the albatross that almost does only flying is related to a penguin, which doesn't fly at all, more closely than the penguin is to its other flightless, similar-looking bird like the Great Auk. So you see where this convergent evolution can kind of trick you into thinking animals are closely related. The auk and the penguin look so similar, you would think they're just cousins of one another. But if you look at the genetics and the evolutionary history, no, they are wildly different animals, and really the penguin's more close cousin is the giant albatross. These are the Ichornithes, or the core water birds: penguins, albatross, loon, pelican. And really, those Charadraformes, they're a totally different, separate thing. Going back to the bird family tree, when we look at the cladogram of all these different birds and how they're closely related, well, even though the auk and the penguin look similar, they're about as closely related to each other as either one is to tiny little hummingbirds. So again, it's just kind of an amazing thing that on polar opposite ends of the globe, those polar conditions, those icy cold waters filled with fish, led to similar selective pressures that developed almost identical organisms from two totally different types of birds. And this is why we can finally answer the question, why are penguins not in the genus Pinguinus? That name penguin was a common name for these flightless seabirds of the North Atlantic. When sailors traveled to the southern hemisphere, they saw similar looking animals, thought they might be closely related, and so penguins of the north became penguins of the south. Around that same time, the Great Auk went extinct, and now in the modern age, all we have to know of penguins are the southern hemisphere penguins. But they're not the true penguins. The original penguin, the Pinguinus impinus, was from the North Atlantic. This is how we know penguins are not Pinguinus. And so if you're ever at a fun trivia night, this would be a good question to ask the group to kind of stump everyone. Hey, what animals are in the genus Pinguinus? Well, it's the penguins, right? Nope. Trick question. Got you there. If the Great Auk went extinct because of transatlantic voyages in the 1500s, what happens when sailors reach the southern hemisphere in the 1800s? Are new penguins also going to go extinct? Well, it could have happened. At the same time, same thing. Just like the sailors of the north wanted to eat the Great Auk, convergent selective pressures mean the sailors of the south also want to eat these new penguins. They would also take the oil from the penguins and they could use it to make things like lanterns. And so for a while, it looked like that same trajectory was going to happen. All of a sudden, we're killing the penguins for food, we're raiding their colonies for eggs. Less and less are reproducing, and are these animals going to go extinct? It was very likely to happen if not for the fact that people realized what happened to the Great Auk was happening to animals around the world. And in the 20th century, we started to put more and more protections in to protect these animals from that exploitation. So the Antarctic Treaty of 1959 and its 1991 Protocol on Environmental Protection, that was a big turning point. These agreements basically banned all the different countries from hunting, disturbing penguins, going to their colonies, and that's what really stopped that exploitation of the animals as a food source. But even into the modern era, penguins still face threats. We might not be hunting and eating them, but we're still impacting the climate. We're still fishing and competing with them for resources. Plastic in the ocean is a problem for all ocean-bound animals, and their icy glacial caps are disappearing, meaning their habitat and where they live is shrinking and shrinking. So even though we're not eating the penguins anymore, we're still not out of the woods. We could face penguin extinction in the near to distant future because of those 18 penguin species today, 5 of them are considered endangered. 4 of them are considered vulnerable, and 3 of them are near threatened. So of those 18 species, about 2/3 are facing significant risk of extinction, and we're monitoring their populations, actively trying to protect them. But it's still up to us. We have to learn from the mistakes of the past, what happened with the Great Auk, and pushing it to the point of extinction, realizing once an animal goes extinct, it really doesn't come back. So if these different types of penguins start to die out, we're going to lose that whole genetic lineage. What did we talk about today? Well, we started with the different naming of animals, starting with Bowen and Linnaeus, how we shortened our polynomial Latin system to a binomial Latin system, creating the hierarchy of taxonomy. And then we also learned about the first true penguins, the Great Auk, the Pinguinus impinus. Now, unfortunately, they did go extinct in 1844, but right around that same time, we found new penguins in the southern hemisphere. And while early sailors did start to exploit those resources, we did eventually realize that protection needed to be put on these animals to make sure what happened to our new penguins was not the same fate as the old penguins.
Hey, look at the penguins!
How different birds are related and how we define these different lineages through things like cladistics and DNA. So I hope you enjoyed that video. It was something I found interesting. I always like the history of nature and science and naturalism. And all of this stuff is things you'll learn in school today, but I think the context of why it came about and why we use these systems is important. And it helps you remember, what this system is. The whole hierarchy of taxonomy, why do we do that? The whole diverging family tree with cladistics. It can all be a lot to take in and try to understand, but I think if you go back to the history of it, why do we do it, it helps learning those things much easier. So I hope you guys enjoyed this particular video. I hope I can make some more for you guys in the future. I love history, I love nature, I love science. So that's kind of what I'm going to focus on with these videos, is just kind of making little fun, informative, educational videos that have some interesting facts along the way. So if you made it this far, thank you guys for watching the whole video. Put a comment down below what your favorite penguin is, or what your favorite bird is, or if there's any fun facts about the Great Auk that I missed, or modern penguins. I like the history of this stuff, but you guys might know even more about those animals in particular. So yeah, feel free to hit me up in the comments below. Let me know what you think, and I appreciate y'all's time, and hope you have a good rest of your day. Thank you.